Hey everyone, so this video is going to be the first infinite series test we're going to talk about, and it's called the divergence test. Some other people, some other textbooks, or other places you may see call it the nth term test, I commonly call it the divergence test, quite literally down to what its definition infers. So if we look at that definition, the test for the divergence test, I should say, basically says one thing. So first off, basically what it's saying here is if an infinite series converges, then it must be true that the limit of the nth term approaches infinity has to equal 0. If that's not the case, it absolutely cannot converge, being that this is a condition. Now, unfortunately, the converse of this, if I were to reverse this, does not necessarily hold true. If it did, then infinite series would be a one-day topic. Because if the limit does equal 0, it does not guarantee that it converges. So we can only really use this test to say something diverges, and then if it actually were to equal 0, we actually would end our thought with no conclusion by the divergence test, and we would have to perform a further test. But the most important thing for this test, as it will help eliminate and save a lot of heartache in some other tests that we learn over the next classes, if the limit as the nth term approaches infinity, if it does not equal 0, then you can guarantee as a fact that it's going to diverge. So the best times to use this test is to always allow this to be your first test. This should always be, and no matter what series you are working with, should be the first test that you try before going on to any further series testing, which we'll get to later. If the nth term is not approaching 0, then it cannot converge, and so this test, again, as I mentioned already, can be used to show, cannot be used, to show convergence. It only is able to tell us if something diverges, okay? Hence the name divergent test. So we're going to take a look at a couple examples here below. Our goal, again, is to determine if the series diverges. If we can't determine that, we're going to simply just say non-conclusive here, all right? So if we take a look at this infinite series, it's n plus 10 over 10n plus 1. I want to decide if this series is going to diverge. So by the divergence test, what I'm going to do is test the nth term as its limit is approaching infinity. And so when I do that, I have this, okay? Now, technically that's an indeterminate form, and we would use L'Hopital's rule. Some in Calculus A, you may have learned that if the highest degree of n is the same, then you can simply take the coefficients as a ratio, and that's going to be your limit. And that would actually work as well. So whichever way you end up doing this, whether you use L'Hopital's rule, and L'Hopital's rule would yield us, it would just yield us 1/10, and of course the limit as n approaches infinity of 1/10 would just be 1/10. Because the answer did not yield a 0, we know for a fact that this series has to diverge. That's why the divergence test is so helpful. It allowed us to immediately say this diverges, and at that point, we know that it adds up to some infinite value that we don't care about, and we can move on from it, okay? If we look at the second example, once again, I'm going to take the limit as n approaches infinity of 1 over 4 to the n power. So if I plug infinity in, if I get 4 to really large, 4 to the 10th, 4 to the 100th, 4 to the 1000th, 4 to the 10 millionth, if it's going to be 1 over very big, and 1 over very big is going to give us 0. Now, because the divergence test only tells us if something's divergent, the fact that it equals 0 means that it could be convergent. And so by the divergence test, this would be actually it would be a non-conclusive series. We would have to perform another series test to determine if this series is going to converge or diverge. Take a look at problems numbers 3, 4, and 5. Please pause this video and try these 3 problems out on your own. Once you have finished, press play and I'll have the solutions up here. So here are the solutions to the 3 practice problems and a couple comments about them in terms of their solutions. So for number 3, if we take a look at the limit as -1 approaches, -1 to the n approaches infinity, what's going to happen here is if we look at this, -1 to the n is going to keep approaching 1 and -1, 1 and -1, 1 and -1. And if we continue to add those up, it's going to continue giving us an alternating value. And so because that value constantly alternates between 1 and -1, 1 and -1 forever, its limit's not going to exist. Since it's not equal to 0, as stated clearly by the divergence test, that means we can conclude that this series has to diverge. As for number 4, it's the natural log of n plus 1 over n. Now, kind of in the same perspective as we talked about on an earlier problem, if I plug in infinity over infinity here, keeping in mind that that is going to give us, when you have the same power in the numerator and the denominator of a rational expression, then you're going to look at just the coefficients. So if I look at n plus 1 over n, that's going to yield in 1 over 1, which means it's going to be the natural log of 1. The natural log of 1 is equal to 0. And so based on number 4 here, based on the divergence test, we can say that, well, we know it may converge, it may diverge, so we have to say it's non-conclusive at this point, and we have to provide further testing to get the answer. Lastly, on number 5, if we take a look at it, we're going to end up with L'Hopital's rule problem, essentially, but there's a shorter way to look at this. If I have 3 to the n, it would be 3 to the infinity, over n to the third, that's also infinity. That's going to give me an indeterminate form of infinity over infinity. However, if I start performing L'Hopital's rule, what's going to eventually happen is n to the third is going to become 3n squared, then it's going to become 6n, then it's going to become 6. 3 to the n is going to yield some more complicated derivatives, but it's going to continually give us infinity in the numerator. Well, as I continue to get those different terms, I'm going to end up with infinity over 6, which would just give me infinity. Another way to look at it is 3 to the n is growing much, much quicker than n to the third power. Hence, this is an exponential, and this is just a cubic. Since exponential is going to outgrow a cubic, that means this is going to always end up winning, meaning this is going to always be the bigger number. That's another reason, or another way to explain why this ends up being infinity. Therefore, we can officially say this is going to diverge.